I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we will discuss about some introduction about genetic algorithm and one example problem for genetic algorithm using 8-Kuhn's problem. All you know that genetic algorithms offer numerous benefits, including global optimization and exploration, allowing them to escape local optima and explore the entire search space. They also exhibit robustness to noise and uncertainty, making them suitable for real world problems with imperfect data. Additionally, genetic algorithms can be parallelized, enabling efficient exploration of large search spaces and speeding up the optimization process. Overall, their flexibility in handling complex problems make them a valuable tool in various fields. In this presentation, we'll see an example problem by using genetic algorithm. Before going into the problem, just we'll see the introduction about genetic algorithm. The genetic algorithm is an optimization technique, optimization method inspired by the principles of natural selection and evolution. It operates by evolving solutions over multiple generations through processes like selection, crossover, and mutation. Genetic algorithm particularly useful for solving complex optimization problems where traditional approaches struggle. By maintaining a balance between exploration, that is searching a wide range of solutions, and exploitation, refining the best solutions, it efficiently finds near optimal solutions. Due to its versatility, GAS, genetic algorithm, is widely applied in various fields, including scheduling, machine learning, game playing, and combinatorial optimization problems like the 8-Kuhn's problem. Now we'll see the example problem by using this 8-Kuhn problem. The first step is the initial population for the 8-Kuhn problem. So in this, we are representing the chromosome representation. The first step involves in solving the 8-Kuhn problem using genetic algorithm is to generate initial population. Generate the, write it, initial, it will generate the initial population. It will generate the initial population of potential solutions. Each solution, that means a chromosome, is represented as an array of 8 numbers, that will see, where each index represents a column, that is 1 to 8, each represents column, and the value at the index represents the row position of the Kuhn in that column. A typical population size can range from, we are arranging from 10 to 100, 10 to 100 chromosomes, depending on computational power and convergence requirements. A large population increases the diversity of solutions but require more computational effort. For example, if we choose a population size of 4, we randomly generate 4 chromosomes, each representing a different arrangement of Kuhns on the board. These initial solutions may have many conflicts, but the algorithm will refine them through subsequent steps that we'll see. This is the example of the initial population, what we have selected, that is randomly generated chromosomes. We are considering 4 chromosomes, 1, 2, 3, and the representations are given 3, 5. So this represents the column, this represents the row. Okay, first column, third row, value, the Kuhn is present here. These are all the values or the Kuhns. Okay, so in this case, how we are going to represent it in the tabular form? First example is what? 3, 5, 3, 5, 1, 8, 2, 4, 6, 7. So 3, where the 3 is present, 3 is the first column, third row. Here Q is present. And the second value is 5. Where it is present, the second row, it is present in the there is fifth column, and here the third value is the third column. It is present, the Q is present in the first row, and the for the fifth value is present in the, that is fifth column. The value is present in here, and next 2, whereas the 2 is present, this is the 2 here, this is 8, this is 2, and 4, this is 1 2 3 4 5 6, this is the sixth column, fourth row, the Q is present. And in the seventh column, where the value is present in the here, present, and last one here, it is present in the eighth row. Okay, so here we are representing the chromosomes are represented in the tabular form like this. Next, we have to find out that is two Qs we have to consider, and where it is hitting, whether it has been hit or not. As far as this example is considered, see here, all 8 here too, this has been, so you know that the queen will move in all the directions. All the directions in the sense, it will move diagonally, horizontally, and vertically. So here this is moving here 8. That is, these two are hitting, and similarly these two are. See here, this is these two here. You erase it. These two are hitting, these two are hitting, and similarly, so all values are being hitted with each other, two columns. We have to find out. First step is we have to for this chromosome. Similarly, for the second representation, 42736851, 4273. So we have represented over here in the column, just to look into. And the third value is what? Third chromosome is 26358174. So we have presented like this, and the fourth chromosome is 53647821. So the fourth chromosome is 7821. It is presented like this. Okay, in this we have to find out the maximum number of Qn pairs. How we are going to find out? By using this formula. There are, how many Qns are there for all 4 chromosomes? We are finding that 8 Qns are there. Whether it is hitting it or not, it has been placed in this table, 8 cross 8 table. 8 Qns are there, and the total number of ways to choose 2 Qns out of 8 is given by the combination formula, that is C of 8 comma 2 is equal to 8 factorial divided by 2 factorial into 8 minus 2 factorial. So this can be written it as 8 into 7 divided by 2, correct? Is equal to, the value is equal to 28. So the best possible for this 8Q problem, the best possible fitness score is 28, which means no Qs attack each other. So no Qs in all 4 chromosomes, either 2 Qs or 4 Qs or 4 sets of pairs are attacking with each other. Our final solution should be no Qs should attack with each other. That we have to find out. So next one is the fitness function calculation. So this is the maximum, that is combination formula, the total number of ways. Here the best possible fitness for the 8 problem is 28. For the given chromosome, what is the fitness value? We'll see step by step. So the second step is fitness calculation. To evaluate the quality of each chromosome, we use fitness function that measure how close the solution is to the goal. The maximum number of non-attacking Qn pair is in an 8Q problem is 8Q problem is given by, so how we have written previously, C of 8 comma 2. This we have written it as 8 factorial divided by 2 factorial into 8 minus 2 factorial. We got the value 28. So the maximum number of non-attacking Qn pairs in an 8 Qn problem is given by C of 8 comma 2. The value is 28, which represents all possible ways to select 2 Qns out of 8 without order. The fitness score is computed as follows. How it has been calculated? The fitness function is equal to, this is the 28, right? So 20 fitness function is found out by how we are finding out 28 minus. So as far as the first chromosome is considered, all pairs are hitting with each other, right? 2 if you are considering 1 2 3. So how many attacks will be there? All 8 are attacking with each other. So we are writing it as, how we are writing the total number of the fitness, the score is given by 28 minus 8. That is number of, this 8 represents what? Number of attacking pairs. All are attacking with each other. So 28 minus 8, the value is 20. For each chromosome, we count the number of cunes attacking with each other along the same row, same diagonal or anti-diagonal, or and subtract this from the 28, right? So higher fitness value indicates better solution, with the perfect solution having the fitness score should be equal to 28. That is no cune. 28 means no cunes attacking with each other. Next is so if you are finding out if you are finding out all these values, for this the fitness score we are getting 28, and in this case 4 cunes are attacking with each other. 28 minus 4 is equal to 24, and here 10, so possible combinations, we are getting 22 in this case. So the next step is the selection. So the first step is what? Fitness function we are finding out, chromosome selection, and chromosome we are finding out, identifying. Next is selection, that is choosing the parent for reproduction. In this case, once the fitness scores are calculated, the algorithm selects the fittest chromosome for reproduction. The most common selection methods what we are using is roulette wheel selection, that is higher fitness equal to higher selection probability, or tournament selection, that is randomly selects best individual from the groups. We are using the roulette wheel method. So the total fitness sum, what we found out here, 20 plus 24 plus 18 plus 22. So this is your fitness sum, 20, 24. For the 4 chromosomes are given. We found out the fitness functions are 20, 24, 18 and 22. If you are adding all those values, we are getting total fitness sum. So the total fitness sum 20 plus 24 plus 18 plus 22, the value is 84. The value is being, we are calculating it as 84. And the probability we have to find out. How we are going to find out? The total value is 84. What is the fitness value for this chromosome 20? So 20 divided by 84, we are getting 23.8 percentage. So we are getting the value 23.8. We are calculating into a percentage. We are getting 23.8. Similarly, the second chromosome, the value is 24. 24 by 84, we are getting 28.6. All you can use a calculator and calculate this value. And the probability of this chromosome 18 divided by 84 is equal to 21 by 4. That is 21.4 percentage. And the last chromosome, we are getting the value 22 by 84. We are getting the value it as 26.2. Correct? So which one is having the highest value? These two chromosomes. The chromosome having the value 42736851 and also 53647821. These two are having the highest value, right? So here mostly likely, more likely to be selected for the crossover, these two parents. The next step is here, in this case, the highest fittest value we are calling it as highest probability. Which one? What are all the chromosomes are having the highest value? So 42736851, the first one, first parent. This we are considering it as a first parent. The second parent is what is the next highest value? 5364. This last one, 53647821. So this we are considering it as the second parent. So the next step is the crossover. Crossover means combining parent genes. So here the crossover is the process of creating new offspring. Process of creating the new offspring by combining parts of two parent chromosomes. A common method what we are using in this problem is the one point crossover we are using. One point crossover, after using this crossover, a random crossover point is chosen at the first part of one parent is combined with the second part of the other parent. So if I am dividing like this, so this value will be moving over here and this value will be moving into this. So after moving, after mutation, this we are calling it as child, that offspring, or we are calling it as the child. So here, see here, child is 4273 and 7821. Next, after reproduction, 5364 and this value 6851. So this mixes the gene to parent, mixes genes to preserve strong traits while introducing diversity. Okay. So the crossover ensures that successful genetic material is passed on while introducing new diversity into the population. So the next step is the mutation. So after crossover, we have to go for the next operator is the mutation. That is randomly altering genes to introduce variations. So mutation introduce small random changes in the offspring to maintain genetic diversity and prevent the algorithm from getting stuck in local optima. So in order to avoid this local optima, we are introducing we are interested in new genes into this. In swap mutation, two positions in the chromosomes are randomly swapped. In random retest mutation, a random position is assigned to a new value. For example, if child 1, so in this child 1, we are introducing 3 5. So in this child, what we are for example, child 1 3 5 1 8 6851, a mutation may change the value 8 to position 6 into 3 here, and resulting okay, here in this case, so the child 1 before mutation 4273, and here we are introducing 5 into this. Similarly, in the second 5364, 6 will be there, and we are introducing 2 into this. So this ensures the diversity, avoiding local optima, improving the diversity. So next step is mutation. After the mutation, generation of replacement, generational replacement and evolution. After selection, crossover and mutation, a new generation is created, replacing some or all of the previous population. A new fitness calculation is performed, and the process is repeated for until multiple generations until the optimal solution is found. The number of generations depends on the complexity of the problem and the size of the population. Typically, the algorithm continue until one chromosome reaches the maximum fitness score of 28 or predefined number of generations. So we will be randomly defining 100 is reached. We are going to stop the algorithm. For example, generation 10, if you are taking 4 to 736851, the fitness score is 24, and generation 50 248 175, and the value is 27. And if you are going for the 100th generation, we are finding out the optimal solution. The fitness is the last step is the solution found out. So after finding out, see here, first column, first row, the value is 1. So 1586, how we are going to write? 1586 1586 3724 37, is that right? Am I right? Yeah. So first column here, in this case, whether you have to tell me whether any hitting is there in this column or not. So the first value, first column, first row is there, and the second column here, the 5, and the third column where here 8, and 6 6 And the fourth column here, it is swapping. This we have to change it. This third column, what it should come here, not this. Third column 8 should come here. This is the queen, and the fourth column it's right. Fifth column 3 should come. Fifth column 3. Here the queen will come. This is the queen Q. I'll write sixth column. So the in this way you have to select, and if you are looking into this, there is no hitting at all for this value. This value there is no hitting, there should not be any hitting in this case. So if it is the case, we are finding out there is no hitting at all in this case. So we can write it. There is no hitting, no horizontal, no vertical hitting is there. So now we are coming into the conclusion that the fitness score, final fitness score is 21. There is no attacking pairs are there. So the perfect solution we found out. Perfect solution we found out. First column 1 in this case, and the second column is so you find out the value for this. So once a solution is found, the genetic algorithm terminates. If no solution is found with a predefined number of generation, the process may be restarted with a different population or modified mutation rate to enhance the diversity. So coming into the conclusion, the genetic algorithm effectively solves 8Q's problem by iteratively evolving solutions through selection. Three operations. What are they? Selection, crossover, and mutation. Instead of exhaustively searching all possible configuration, it intelligently explores the solution space, gradually improving the population's fitness. By balancing what is happening? Exploration, searching new possibilities, and exploitation, refining promising solutions. The algorithm efficiently finds an optimal arrangement where no two queues attack each other. No queues attack each other. We have to find out the solution. With appropriate tuning of population size selection procedure, right, and crossover rate and mutation rate, genetic algorithm can reliably reach a valid solution within a reasonable number of generations. So these are all the conclusion about the genetic algorithm using 8Q problem. Hope everyone understood the problems of 8Q. By using the genetic algorithm, the remaining things we'll discuss in the next class, next lecture. Thank you.